I will begin with a word of prayer. Dear Heavenly Father, we thank you for this day. And I just thank you for this class, Lord. Help us to just glorify you, what we do, Lord, this day. In your name I pray. Amen. So we're mostly talking about splitting fields today. I will just say one word about your homework, since I kind of glossed over section 13.3 on, classical straight edge compass constructions. I think to do your homework, all you really need is just to carefully consider the impact of Proposition 23. Proposition 23 on page 533 says that if a real number, all right, is obtained by a series of compass and straight edge constructions, all right, then alpha in the reals constructible in the classical Euclidean compass straight edge sense, then the here I'll specialize the proposition to the rationals, but the extension field of alpha is over the base field, such constructible number. Oops. Well, that's equal to 2 to the power k. So basically, if you can show that the thing you're trying to construct amounts to, having an irreducible cubic or something, well then you can't construct it, right? Because an irreducible cubic does not arise as an extension. The number that's degree 3, for example, can't appear in this sense because, your options are, well, just a rational number, obviously, but also, like something like the square root of 3 you could construct, right? But not the cube root of 3. And then also, you can't construct transcendental numbers. So your two homework problems, one I think is it amounts to an extension. Anyway, it violates the 2 to the k extension. Both of those homework problems that I've assigned you, I think you can do by contradiction. And the spirit of the proof is probably fairly similar to the theorem 24. For example, doubling the cube amounts to constructing the cube root of 2 in the real starting with unit 1. But since the extension field q adjoining cube root of 2 over q is the degree of that extension is 3, and 3 is not a power of 2, this is impossible. I mean, that is the kind of, you don't have to understand, to actually understand everything that led up to the construction of Proposition 23, it's somewhat involved. You'd actually have to be a good Euclidean geometer. But if you use Proposition 23, you can be relatively ignorant of the rest of the section and still be successful in doing those homework problems. I didn't want to remove them because I think it's important for you guys to be aware of this. I think it's interesting stuff. All right. So moving on to section 13.4, let's think about this. If we have f of x, right, a polynomial over a field, right, then there exists an extension field over f in which alpha in E, right, is a root of f of x. And so we get f of x is equal to x minus alpha times g of x for some g of x in E of x, right? This is the construction we've talked about the last couple classes. You look at the factor ring mod by, you can find an irreducible factor of f of x and mod by that. Then you'll get a 0, right, for that irreducible factor, and hence a 0 for f. Okay. And what's the degree of this extension? The degree, if we look at E, right, over f, is, what's the degree of E over f? Now let's suppose that f is degree n. guys with me? So what would that make g of x? N minus 1, right? So if you think of it, let's see here. What's the degree of E over F in this construction? At most what? I mean, it could be that f of x is irreducible, right? So if f of x is irreducible, you know, sidebar, if f of x is irreducible, then what did we do? We did the polynomials mod the principal ideal generated by f of x, right? And this was essentially our model for E, right? Where we're identifying f as the you know, constant polynomials in this factor ring, right? And the alpha here essentially is x. Alpha is equal to, you know, x plus f of x. That element, when you evaluate a polynomial over that factor ring, evaluated at alpha, that's by construction going to give you 0, right? Because essentially this quotient has f of x equal to 0. So it makes that alpha be the 0 in that quotient. So if f of x is irreducible, then we have learned that the degree of this extension is what? It's n, right? But f of x, you know, little f of x doesn't have to be irreducible. So it could be, you know, it could be anything less than or equal to n, right? Let's see here. Can you guys think of an example? Let's just, before I even go on and do anything more, let's just make sure we all understand what I'm talking about. So here's a silly case. You could have something like f of x equal to x squared minus 3x plus 2 in the rationals, right? See, but the thing about this is what? This is x minus 1 times x minus 2, right? So if you form an extension in this way, right? If you extend the rationals by trying to mod by, you know, f of x, what are you going to do? You're not going to add anything new, right? Your extension is just going to be the rationals again. So despite the fact that f of x has degree 2, the degree of such an extension would just be 1. It's kind of silly. On the other hand, you could have something like, you know, f of x equal to x squared plus 4x plus 5, right, over the, let's say, reals, just for the sake of switching it up. And you know what happens here. This is x plus 2 squared plus 1. So that has zeros of alpha equals to minus 2 plus or minus I, right? Of course, those are not in the reals, so if you look at an extension, in fact, this has no real zeros, right? So in this case, if we look at the extension field, we're going to get 2, right? If we build the extension in that way, in terms of R of x mod, the principal ideal generated by this polynomial. Okay, are we good for the first step? So then you keep going. Suppose you keep going with the initial process, right? So you got this, let's call it E1. Right? So suppose we've got f of x equal to, you know, x minus, and maybe I should call it alpha 1 just for the sake of discussion, right? I got enough ones. well, there's no need to be 1 here. Okay, so x minus alpha 1. I guess I probably should put a 1 on the g too. Sorry, big silly. Then, well, if g1, well, then we can consider doing the same for g1 of x, right? You can find extension E2 over E1 in which alpha 2 is in E2, right? And that factors g1 of x into x minus alpha 2 times g2 of x, right? Now the degree of g1 is n minus 1, right? So this, if we look at the E2 extension over E1, right? So what's the degree of E2 over E1 going to be? Less than or equal to what? How about this? If G2 is if G1 is irreducible in E1 of x, right? Or if G1 of x is irreducible over E1 is our language, then that means the degree of this extension E2 over E1 is what? It's n minus 1. But that doesn't have to happen, right? It could be like this, where when you extend by 1, you know, well, I guess we're looking at a degree 2, so yeah. Well, anyway, I'm digressing here. So yeah, at most n minus 1, right? At most n minus 1. So you'd have, you know, at this point you'd have f of x equals to x minus alpha 1, x minus alpha 2, g2 of x, right? Where g2 of x is where? It's in the second extension in principle, right? And then you do this again, right? When you extend G2, if G2 of x is irreducible, then that means the E3, yet written, would be degree n minus 2 over E2, right? So we can just keep extending and extending and extending, each time peeling off or generating a new linear factor in the new extension. But this process has to terminate, right? Because it's degree n, and we can have at most n zeros for a nth order polynomial. That's a general result. No matter how weird and abstract our fields get, we have at most n zeros. Because the factor theorem is general, right? To each zero, there corresponds a linear factor. At least one of them, right? I mean, you could have, of course, you can have something like a repeated zero. And that's actually the subject of section 13.5, is on separable, which is on repeated roots. And then the derivative appears as to picking up the repeated zeros and things. We'll get there. So anyway, let me just get to it. Basically, the point here is that there exists E, right, over F, such that what? Such that f of x is equal to, I mean, in principle, some constant, x minus alpha 1, x minus alpha 2, x minus alpha n, right? So in principle, there exists an extension over f, which contains n zeros. And you know, so these zeros are in this ultimate extension. And what's the degree of E over F at most? I mean, in my construction, it's going to be equal to the degree of E. Let's see, how many times do we extend? If you keep going on with my counting. I guess n times, right? The nth would be E sub n. So it's like E sub n over E sub n minus 1 times E sub n minus 1 over E sub n minus 2 dot, 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 E2 over E1, E1 over F. By the multiplicative, I mean by the degree of compound extension formulas we discovered last time. Right? But then this is about the closest we're going to get to analysis. This is less than or equal to what? Sorry, this is my, I don't know if a guy told you, my glib characterization of algebra versus analysis is that algebra is about equality, whereas analysis is about inequality. Now this is, of course, very overreaching and grossly simplifying, but So look, we're doing analysis. I think that kind of shows you the error in that statement already, yeah? But so this actually is just at most degree 1. This is at most degree 2. And that's at most degree n minus 1. This is at most degree n. This is degree n when the initial polynomial is irreducible, right? So we have n minus 1, dot, 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 2, 1, less than or equal to n factorial. So you can always keep extending until you have the polynomial factored into linear factors. This is possible. You just have to keep extending. That brings us to the definition. I mean, this is actually later in section 13.4. I switched it up a bit because I think this is a good calculation to do from the outset. So definition, f of x in f of x is split over, well, let me say this, has splitting field E if f of x is equal to, a times x minus alpha 1 dot, 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 x minus alpha n for alpha 1, alpha 2, dot, 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 alpha n in E. Oh. Candy? I don't know. I pushed the lectern back a bit, and I've uncovered some snack. All right. Now let's see here. The wording he uses in Dumb and Foot, it says an extension field k over f is called a splitting field if f of x factors into linear factors in k of x, and f of x does not factor in any proper subfield of k containing f. So I just wrote out what that means. Here's linear factors, right? A is an F, I think. I think A has to be an F, just if you think about it, because if you multiply that out, the leading coefficient is ax to the n. And since f of x is assumed to be a polynomial over f, that means A has to be an element of f, yeah. And f of x does not factor in any proper subfield of E. So this is the so-called splitting field of E. All right. Now, I kind of just gave you a constructive proof that there exists this splitting field, right? But theorem 25 just states what? Theorem 25 says for any field, if f of x is a polynomial over the field, then there exists an extension k over f, which is a splitting field. Now, there's nothing about degree there. And what he does is he gives an inductive argument on the degree to prove that the splitting field exists. All right? Let me just talk through the inductive argument of theorem 25. If we, so theorem 25 is a weaker version than the result I just said. Let's talk about the proof, though, because it's kind of an interesting method of proof. Given f of x, in f of x, there exists k over f, which splits f of x. So the proof of this theorem 25, again, I think we already have this result constructively by this argument of repeated extension, but constructive proof, although, well, I'll shut up, by induction on the degree of f of x. So first of all, think about n equals 1. N equals 1 is stupid, right? N equals 1, if you have a polynomial of degree 1, is it factored into linear factors? I mean, it is a linear factor. So yeah. So suppose inductively that this theorem 25 is true for any polynomial up to degree n minus 1. Okay? Use strong induction. Suppose you have a polynomial of degree n, right? If it's already split linear, if it's already factored into linear factors, then you're done. It's split linear. If it's not factored into irreducible linear factors, we know, by the way, from last semester that f of x is a polynomial over a field, right? So by the unique factorization theorem, f of x is u of d, there exists a factorization of f of x into irreducible factors. So if they're not all linear, that means by degree considerations, there has to be one of degree larger than or equal to 2. So then you can look at the quotient by f of x mod that irreducible factor, and that is an extension of degree what? At most n minus 1. I mean, it can't be, that extension has, it's not going to have degree n. The irreducible factor could be up to, I mean, you might have the case that the irreducible factor has to be n minus 1 degree is the thing. It's less familiar to us. But that could happen. But that's no problem because that's a degree n minus 1 extension over f, which then we can apply the induction hypothesis to get a factorization. And then the other factor would just be the x minus alpha 1 from the extension. Then by induction, that proves it for all polynomials in all degrees.
And in the book, he just divides by the x minus alpha, and then he doesn't need strong induction, he just uses regular.
Yeah. Exactly. He does not use the strong induction. Very good. Next definition, he says, if K is an algebraic extension of F in which the splitting field, which is the splitting field for a collection of polynomials, then K is called a normal extension. And then he never talks about it again. So I'm not going to write it down. Okay. So let's look at some examples. One, x squared minus 2 over q adjoint x, right? Splits where? In q adjoint the square root of 2, because you notice that x squared minus 2 is equal to x minus 2, x minus root 2 times x plus root 2, right? And plus or minus the square root of 2 is in this extension field, right? And of course, you have proved from time immemorial that the square root of 2 is not a rational number, so you know it doesn't split in Q itself. And since it splits in this extension field, we don't need to look any further. That's the, that's the smallest, well, I guess that's the, what to say here. Anyway, that's the splitting field for x squared minus 2. I don't want to say more. There's no more to say here. All right, 2. If we have the product x squared minus 2 times x squared minus 3, right, then we can look at q adjoin square root of 2, square root of 3. That's a splitting field for this. Let's see here. Now, so the field diagram, I think, is interesting, though, right? I think left to my own devices, I might only think of the outside of this. I mean, it's obvious to me that q adjoin square root of 2 and q adjoin square root of 2 seems wrong. 3. Indeed. That's the thing I might not have thought of, but in fact, of course, in the field which contains root 2 and root 3, we can multiply them, right? If you really look at what we're doing in this section, so much of the non-trivial calculation goes back to that simple proposition in the section 13.2 that said if you have alpha and beta in a field, the product of alpha and beta, the difference of alpha and beta, the quotient of alpha and beta, beta not 0, are again in the field. That guides so much of the calculation. The non-obvious calculation, I would say. So yes, q adjoin square root of 6. And then, of course, over this, these are all extensions of the rational numbers. What's interesting here, I think, perhaps, is that, I don't know how interesting it is. This is a degree 2 extension. This is a degree 2 extension. This is a degree 2 extension. And, by the way, this is the splitting field. This is the splitting field for a degree 4 polynomial, right? So what does that say about the degree? What can we say about the degree of root 2, root 3 over q? Oh, I guess we could say it's less than or equal to what? 4 factorial. Which is otherwise known as what? 24. But of course, what? I mean, this is degree 2, this is degree 2, this is also degree 2. So in fact, this is really just degree 4 over the rationals because well, really because if you look at x squared minus 2 in q adjoin the square root of 3, x, right? Look at this polynomial in there. Then x squared minus 2 is irreducible over q adjoin square root of 3. And remember that this is also fundamentally the extension like this, right? That's taking q adjoin root 3 and adjoining root 2. That's what that is. And we have that identification. So we're adjoining root 2, which is a degree 2 algebraic number over this field, because that's irreducible. I'm not sure I've actually proved that here, though.
I feel like I'm just misremembering because I seem to remember something from like the first day of class when we were talking about how we adjoin 2 elements that we can form an equivalent field by just adjoining 1 element. Is that wrong?
No. Yes, it is in fact also true that this is q adjoin c for appropriate c. In your homework, you're asked to prove that q adjoin square root of a square root of b is actually q adjoin square root of a plus b square root of b, if I remember right.
Is there a reason that the book doesn't do that here, just because it complicates things?
I think it's just a distraction at this point. Yeah. The general theorem Galilean calls the Steinmetz theorem. It's from like 1910, that any finite extension actually can be written as what's called a simple extension. So this appears not to be simple because it takes adjoining 2 elements, but actually, if you were to look at the square root of 2 plus the square root of 3, you can get all this stuff. But yeah, certainly a more verbose version of this section should include that as a theorem. But I think he'll get around to it, if I had to guess. We lost our king. I was thinking instead of the wrath of Khan, the math of king. Let's see here, sorry. I need to make sure he watches that so I can explain this joke to him. All right, where was I? Oh yeah, we don't need this anymore. All right, next up, next example. And this is an important example, is looking at x cubed minus 2 over q. So, if we let alpha equal to the cube root of 2, then clearly alpha cubed minus 2 is equal to 0. By construction. I mean, that's the third positive. This is a real number, okay? Let's see here. But complex. Let me use a little bit of complex analysis if you don't mind. So complex tells me that if I want to look at solutions to x cubed minus 2 equals to 0, all right? Then what I can do, in other words, I'm looking for solutions to x cubed equal to 2. The solution set to this is that x is an element of the third roots of 2. The third roots of 2 actually is equal to, well, alpha times zeta 3, alpha times zeta, I can't write it, zeta 3 squared. Now here, this zeta, unit circle, all right? So here's 1. Here's zeta 3. Here's zeta 3 squared. Zeta 3 is the exponential of 2 pi I over 3. We talked about this the other day, of course. This is minus 1 plus I root 3 divided by 2. So if I was to say let theta 1 equal to the cube root of 2, theta 2 equal to the cube root of 2 times minus 1 plus I squared of 3 divided by 2, and theta 3 equal to the cube root of 2 minus 1 plus I root 3 over 2 squared. What is the square of zeta 3, though? Let me just be less. Let me not write the square. Let's just write what it is. What is that? Look at this. These have to be, these are complex zeros to a real polynomial. Well, rational, but it's real also. So they have to come into conjugate pair. So you see zeta 3 squared has to be zeta 3 conjugate, which is to say, we just put a minus here. Anyway, depending on how explicit or not you want to be, the point is we have that x cubed minus 2 is equal to x minus theta 1, x minus theta 2, x minus theta 3. So certainly a splitting field here, if we let k be q adjoin theta 1, theta 2, theta 3, that is certainly a splitting field for x cubed minus 2. But then the question arises, as you guys are starting to ask about the last example, is that the best description of the splitting field? Can we give a better description which is easier to analyze? Yeah, we can do better. So we go back to the last section that talks about getting elements of a field from a given pair. So how about this? If we look at the ratio, if you look at the ratio, theta 2 over theta 1, what do we get? we just get minus 1 plus I squared of 3 divided by 2, right? But this implies that 2 times theta 1 over theta 2 plus 1 is equal to I the square root of 3. But if you look at the left-hand side, if you take twice the ratio plus 1, remember that 1 is a rational number, which is by construction in K, we again have a K element. So this shows you that I times the square root of 3 has to be an element of the splitting field. And of course, we already have that the cubed root of 2 is an element of the splitting field, right? And if you look at it, we can build theta 1, theta 2, and theta 3 from nothing more than the square root of minus 3, or I times square root of 3, right? Now, thumb and foot is tending to write this as a square root of minus 3, and that's fine. Okay. So the square root of minus 3 and the cube root of 2 adjoined to q gets us theta 1, theta 2, and theta 3. So in fact, this is equal to q adjoined the cube root of 2, square root of minus 3. Now that's nice because it allows us to sort of analyze the degree. If you get into the weeds here and you want to prove irreducibility of one part of the extension over another, then you've got much nicer polynomials to look at, right? Like, for example, the square root of minus 3 is attached to what? Like x squared plus 3 is its minimal polynomial, right? Whereas the cube root of 2, what's its minimal polynomial? Something like x cubed minus 2, right? I'm being intentionally vague. You might say over what field? I don't know. I think that works for any field where you can ask the question. I mean, I don't know. Okay, so getting to the story here, we have Q adjoin the splitting field, K, Q adjoin cube root of 2, and the square root of minus 3. And of course, that's over Q adjoin the square root of minus 3. But it's also over this guy, right? And it's over this guy. And it's over this guy. Those are all subfields of the splitting field, where theta 1, theta 2, and theta 3 are as I wrote them here. And then, of course, these are all extensions of the rationals themselves of various degrees. So this is a degree 2 extension, right? These are all degree 3 extensions. Right.
So the book says all known diagonal subfields. Are there other subfields besides these? Seems like you form the square root of 3 itself, unless you can.
I don't know if there are other subfields defined here. I know there are in the x to the p minus 2 example. He just draws the diamond. And that diamond expands like this for p equals to 3. Later he's got this x to the p minus 2, and he just draws. Basically, his top is q adjoin the pth root of 2, the pth root of unity, right? And then over that, he has the extension by, curses, what is that? I lost my stupid thing. Yeah, yeah. Now that's definitely a partial diagram. This one I'm not sure if there's anything else out there. If you think of something, we'll put it as a comment to the video later. Since you're no longer able to put annotations in the middle of videos without actually going in and editing them yourselves. YouTube used to have tools where I could stick on like a bubble that would say, hey, the other root's blah.
Yeah.
No longer.
Well, but here we didn't include the zetas in the diagram, right? So would that mean that it's
Well, this is,
because we can't form.
well, the thing is, it's kind of,
Is that equivalent to?
yeah, I mean, exactly. That's one of the things. Oh, thank you. You've drawn out a thing I wanted to say today, and I would have regretted not saying. This is the kind of surprising thing, is that this is in fact equal to
Oh, right. No.
Q join the third root of unity, which is something that was non-obvious to me yesterday.
Right, because you just, yeah, it's the same calculation we just did.
In fact, I called my brother to say, there's a typo in this book, and Bill's like, no, no, no. Look, this is zeta 3 plus a half is equal to I root 3 over 2, which says that I root 3 over 2 is in the field that it's Q adjoin the third root of unity. So it's, yeah. Don't be so quick to assume you're wrong or they're wrong. It could just be like a really sneaky different way of writing the extension field, yeah? All right, there's something I want to say here, though. So since, let's see here. Looking, let's look at this right here, this one. So if you look at that, we have, what are we doing? We're adjoining, what are we doing? We're adjoining the square root of minus 3 to Q adjoin the cube root of 2, right? So that's an extension field. And you notice that we have x squared plus 3 in the polynomials. Here. So that means that k over q adjoin the cube root of 2, right? What's the degree of this extension? I mean, square root of minus 3 is a 0 of this polynomial, right? So if that's, either that's irreducible or some factor of it's irreducible. Either way, the degree of the extension is at most what? At most 2, right? Now, can it be 2? What would it mean for it to be 1?
It would mean that you can generate a complex number using real numbers.
Exactly. Right. Implies C is obtained from R via arithmetic. Yeah. Which is, of course, a contradiction, right? Which means that, in fact, that's not less than or equal to 2, it's equal to 2. But on the other hand, what else do we know? We know that, from the start of today, what did we learn? With the extension of k over q, right? What's the degree of that? It's the splitting field, right? It's the splitting field for a degree 3 polynomial. So its degree is at most what? It's at most 3 factorial. But you can see that it has what? If you look at this, the degree, 3 times 2 gives us that the degree of this is at least 6. Well, actually, I think this right here would actually, well, let's forget it. Let's suppose we don't know this, right? Erase this 3. Erase that 3 for a second. What do we still know? We know that if we erase that 3, we know that 2 divides the degree of the splitting field. Do we have an argument that says that 3 divides the degree of the splitting field? Well, this is a degree 2 extension. I guess it doesn't give it to me. I'm trying to think here.
Is there a better way than just saying the cube root of 2 is irrational?
Well, the cube root of 2 being irrational does it, doesn't it? The cube, exactly. Oh, I'm sorry. Let me not erase that. So, anyway, let's not erase basic things that we know. Sorry. So you put this together, we have the degree is less than or equal to 6, and also, well, let's see here. Another way to look at this, erase the 2, right? I'm still, I don't know. We can gain, if you establish enough of this, you can fill in one of the numbers from the remaining ones is the point. And I'm not making it very clearly. But anyway, this splitting field does have degree 6 over the rationals. Let me go on here. But beware. Oh. There, of course, is... well, first of all, this one here, if P is prime, we can look at the splitting field of this one, right? Another example is this one. As you just said, the Pth root of 2 is irrational, right? Math 200. So that would prove that this is a degree what extension? Or would that prove that? Well, this has degree d not equal to 1. That much we can say. But I yes, that does have degree p minus 1. How do you know that? Oh, yes, but there's something that, so Pth root's a unity. Let's look at that for a second here. So basically you're solving x to the p equal to 1, right? Which is really x to the p minus 1 equals to 0. And so that factors into x minus 1 times x to the p minus 1 plus x to the p minus 2 plus plus x to the x squared plus x, plus 1 rather, right? And while this is not true, I mean, in fact, this calculation, if you forget about p being a prime, it's still true, right? But for p being a prime, we can prove that this is irreducible. And in fact, that's what's, I think Vp of x is this thing, right? Well, let me be careful here. But the point is that's irreducible. And so in fact, you're right, it is a degree p minus 1 extension. And in fact, if we thought about it carefully, we would get that this extension over here has degree p, right? That's in fact true. So because p and p minus 1 are relatively prime, and they're both subfields of the splitting field, right? The one that has adjoined the p through to 2 and the p through to unity, it follows that the field upstairs has degree what? It has degree p times p minus 1 over the rationals. So next time we'll look at the so-called cyclotomic fields, which have to do with adjoining an nth root of unity to rationals. Right? This gives us a very pretty field extension of the rationals. And ultimately, the major theorem at the end of the section basically shows that there is this field out there in which we can adjoin the zeros for not just one polynomial, but if you look at all polynomials over a field, there's just like big mega field out there, the algebraic closure, in which there are all polynomials split over a given field. But this involves an application of Zorn's lemma. And well, I won't actually go over that proof in class. If you want to read it, that's good. But the proof at the end of the section by Artin is very pretty. It involves this sneaky contradiction proof to prove this particular ideal is not proper, and then as such it's contained in a maximal ideal of some ideal. Then you mod by this maximal ideal, it gives you a field that's out there somewhere. In that field out there somewhere, you have a 0 for an arbitrary polynomial, and it's very sneaky. But anyway, the algebraic closure is out there. You can find it. And so anyway, I will try to do a few more examples from this section before I go on to the next, but hopefully we'll be into the next section next time. Just I've got a little bit more here to do. Thanks, guys.